we're gonna record a new material now, folks. See if it's live. Yes, it is. So today a mixture of topics. In fact, it's the same topic but different points of view. We will corroborate these points, these different points of view, as we get to the fundamental theorem of calculus. Until then, so we're going to do two things. First of all, the first thing is going to be a quick review of the antiderivatives just to make sure that you don't forget them. That's number one. And number two, we're going to do something new, some area calculations, which apparently have nothing to do with antiderivatives. So as I said, they are connected, and we are going to see the connection a little later in the week. So this week, we're gonna go over those important topics. All right, so first of all, let's go here and let me share this with you. So come on, sharing button. All right, there we go. So the sharing button here, and I'm sharing this with you, folks. So what we need here is 3.9. So we 3.9 antiderivatives. And I'm really doing this just to review, folks, because it's been this kind of, break in the cycle, and I don't want to have a long break for this. So a quick review here. So remember that the antiderivatives of and when we have x to the n, well, n here, that's going to be 1 over n plus 1 x to the n plus first. That's the antiderivative for x to the n. Okay, okay, so that for cosine x, remember, folks, the antiderivative is sine x because sine prime is cosine. And for sine x, the antiderivative is negative cosine x because the derivative of negative cosine is sine. So these folks, these things these things here that I'm doing right now, this everybody should know. I think we should also maybe include secant squared, whose antiderivative is tangent x. Just, to have a complete, more complete, table. It's not really complete here, but these are the key ones, and everybody should really know these things. Now, besides these things, you should know how to operate with these, and I am going to review for you folks here a problem from the book that does exactly that. And that problem is number 17. Now I'm going to do number 17 here, 17 of 3.9. Again, it's just a review problem. So number 17, f of t, I'm going to say t instead of the Greek letter t, which is theta, is 2 sine t minus secant squared t. All right, and the antiderivative, folks, antiderivative of this function is for the 2 sine t, the antiderivative is, again, remember, folks, for sine t, the antiderivative is here is negative cosine, so this guy is going to be negative 2 cosine t. And for minus secant squared, is going to be tangent, so minus tangent of t. So that's going to be the antiderivative. And remember that at the end of the day, you have to put this extra constant plus that constant c. All right, so these are the antiderivatives, and this is the antiderivative of this entire thing here. Okay. Now, the next thing that I want to do here is the following. And the next thing is I'm going to do a problem where you are going to look at an antiderivative, but this time around with some initial values. So these, again, these problems are not particularly important for us in this class and perhaps not even in calculus 2, but they would be important, for instance, in calculus 3. I don't know how much in calculus, so now it depends on the instructors in calculus 2, folks, but calculus 3. So you will have these kind of things, you will have these kind of things in differential equations for sure. So let's do, and I'm gonna do here, folks, number, which number did I say here? So one second. Oh, number, yeah, 38. Number 38 over here, folks, from section 3.9. So this is again a review problem where f prime prime of t is equal to 4 minus 6 over t to the 4. F of 1 is 6, and f prime of 2 is 9. And then t is greater than 0. So f prime prime is that. And now let's do, again, this is a question that's very much in lockstep, if you want to, if something that you do in physics at some point. Now I don't know exactly when, but in the class where you do physics based on calculus, because there's two different types of physics we teach here. The beginning level of physics is physics, algebra-based physics, and calculus-based physics. So in the class where it's called calculus-based physics, you for example, you say, oh, okay, so the second derivative of a displacement function is gravity, because that would be the case when you throw stuff in the air. In other words, throw a rock or a ball or something, a baseball or something like that. So in that case, that motion is governed by the derivative by gravity. And gravity is the second derivative of displacement in the vertical direction. There's horizontal direction, of course, but in the vertical direction, the displacement is governed by gravity. And of course, the initial position is important, because that's one thing. If you hit a baseball, for example, from a height of 2 feet, and there's another thing if you hit a baseball from a height of 1 foot. And also the initial velocity. So you hear these people if you watch baseball games, so the pitcher, or the batter, they hit the ball at I don't know, 100 miles per hour or something like that. So those two elements are very important: the initial position and the initial velocity. Well, they are described in my case. If I call my function f, they are described by these two. F of 1 equals 6 really represents the initial position of the graph of this function, and f prime of 2 equals 9 really represents the initial velocity or the tangent function. Well, initial is kind of a relative term here. The tangent function at a point 2 seconds after the hit. But so the bottom line is there's some data that identify this function uniquely. And of course, the most important one is this one that tells us the second derivative. And this is what we're going to use, folks. And I explained last time, we're going to use these step by step. So we're going to say first, oh, f prime is the antiderivative of f prime prime, because f prime primed with the, so the derivative of f prime is f prime prime, but because f prime prime is 4 minus 6 over t to the 4, f prime is so now f prime is equal to 4t, remember? So we do the antiderivative of 4, which is 4t, and now for here, so remember that negative 6t to the 4, this is the same as, if you want, we can write this thing as 4 minus 6t to the negative 4. Very important here, folks, to be able to recognize that the function can be written like that. Again, we don't want denominators. And when we do the antiderivative, 4 is 4t, 6t to the negative 4. The antiderivative of that will be negative 6 times. And we're going to say, oh, it's t to the negative 4. Very good. So, so the antiderivative is t to the negative 4 plus 1, right? So we add 1, which is negative 3. And then over here, we multiply by 1 over negative 3. Now, luckily, these numbers cancel out nicely, and we end up with 4t plus 2t to the negative 3. And don't forget, at the end of the day, plus a constant c. So this is our first derivative. Okay, now the formula for the first derivative is not complete because of this constant c. But we know something important about the first derivative. We know that f prime evaluated at 2 is equal to 9. And you see how that nicely falls into place here, because we can say, oh, it's 9, but we also know that the formula for the derivative f prime is 4t plus 2t to the negative 3 plus c. So we are going to substitute 2 in the formula for t. So that's 4 times 2 plus 2 times 2 to the negative 3 plus c. And if we calculate on this side of things, we have 8 plus 2 over 8, which is 1 over 4. 8 plus 1 over 4 is 8.25, let's say, plus c. So it will follow, because 9 is 8.25 plus c, it will follow that c is 0.75, or if you want, 3/4, like that. So let's write it as a fraction. It doesn't really matter. I'm just playing with the numbers here at this point in time. It's not so important. But the important thing is that f prime of t, folks, and we can write a nice formula here is, so let me make this bigger a little. Okay. So is 4t plus 2t to the negative 3 plus this constant here, which is 3/4. That's very important. Because at this point in time, I can do yet another antiderivative, and I can say that f is the antiderivative derivative of 4t plus 2t to the negative 3 plus 3/4, which is 2t squared. All right, so the antiderivative for 4t, folks, is 4 times t squared over 2, or 1/2 t squared, plus the next thing here. So we have plus 2 times, and we have t to the negative 3 plus 1, which is negative 2, times 1 over negative 2, folks, plus, and for 3/4, because that's a constant, 3/4 t. And then again, at the end of the day, plus so that simplifies. Let me just say what that simplifies to. That simplifies to 2t squared plus minus, I should say here instead, because t over negative 2 is minus t to the negative 2 plus 3/4 t plus a constant c. Now, folks, this constant c is, well, you know what? I don't want to confuse you. So that's another constant. You know, it doesn't have to be called c. So let's put another name of a constant. Let's a constant k. There we go. That's a different constant. So this constant k, I'm going to write on the next page. So 2t squared minus t to the negative 2. So f of t is 2t squared minus t to the negative 2 plus 3/4 t plus a constant k. And what we know about this constant k is that, well, we know that f of 1 is 6. And again, that falls nicely into place for us, because if f of 1 is 6, well, we can just substitute 1 here and solve for k. So that's going to be 2 minus 1 plus 3/4 times 1, right, plus k. And if you solve for k, you will see that that's 1. Okay, so 6 minus 1 is 5, minus 3/4, 4 1/4. So k is 4.25. All right, folks. And with that in our bag of tools, 4.25 is, by the way, you can write 17 over 4 if you want. It's not pretty. So I'm just going to keep it this way. So f of t, I can say, is 2t squared minus t to the negative 2. Now, for uniformity, I'm going to make 3/4 0.75t plus 4.25. So this is pretty much what you will do in physics, folks. At least that's going to be one of the exercises that you will do in physics. So you will try to recover the trajectory of a rock or a baseball or something like that based on the initial data, the initial position, initial velocity, and gravity. So this is the end of this particular lesson. Now, if you folks have any questions for me, I'm going to stop sharing this screen here. Let me know, because we're going to move on to a totally different topic. So this was a review if you want. This is something that's going to be on the next quiz, which, by the way, is coming up pretty soon. So it's going to be not this week, next week. So that's this topic, and also antiderivative. So 3.9 will be a key focus for us in the coming quiz. So what I'm gonna do next for the remaining part of the hour, I'm gonna move on, and I'm gonna start chapter 4, and we will start with the first lesson in chapter 4. I'm turning the page here, and let me just okay, copy the correct title, section 4.1. So okay, so that's going to be our first thing here, and section 4.1. I'm going to move the page here. Section 4.1. Oops, have all of these things here on the screen. Section 4.1. Well, so that's going to be a discussion about areas and distances. Now, curiously enough, so somehow the author of a book makes it look like this discussion about distances and such would be more or less related to the discussion about areas, and it is if you're looking a certain way at things here. But I want to point out that it's they weren't treated the same way with the same attention. In fact, all this discussion that we carry out here really had to do with the areas, and then distances, were cleverly thought of, in terms of antiderivatives. But areas were the first ones that really drew the attention of mathematicians, and they were investigated, and that's what led to these concepts that we discuss here. So mainly we will focus on areas. If we have time, I will mention something about distances. Here's the deal. So let's say you want to calculate an area of a triangle. And if you want to calculate an area of a triangle, let's say the triangle is ABC. Yep. So it's not fairly obvious what a measurement would be. So the only one that's obvious would be a rectangle, right? For rectangles, we more or less can sort of come up with an intuitive idea by saying, you know what? If I cut thin slices in this rectangle and they all have the same length, a good measure for this thing would be to multiply the length of the base, which would represent how many slices I have here, times the size of a slice. So that takes us to the notion of area for a rectangle, which is base times width. or base times height. It depends on the terminology or when you learn it or how you learn it in school, in high school or so. So this is the area for a rectangle. So for a rectangle, it's pretty clear what the area would be. But for a triangle, how do we relate this one with this one over here? Well, there's a clever way to do that. I'm going to explain you that quick way here, and we'll see how much we can actually pull these tricks to find something more general. So here's the trick to do that. So I'm going to drop a perpendicular. So I'm splitting this in two. These are not necessarily equal areas, and in fact, in most of the time, they are different. But that's okay. So the next thing that I'm going to do, I'm going to try to complete a rectangle over here. Now, now the reason why this works in a rectangle over here on this side. The reason why this works is because you can think of this as made out of paper, and then you cut it over here and you fold it exactly. You kind of take the symmetric of that if you want, and you take that piece of paper and you arrange it the other way around. In other words, this base here comes over here at the top, and this vertical side stays vertical side here. So if you look carefully at this picture, this area, the shaded area here, is equal to the area of a completed rectangle, the triangle here. So the one that completes the rectangle. So this one twice, so this area that I put here twice will give you the area of the rectangle over here. So the area of this rectangle that I'm going to shade with, let's say, a different color, let's say red, is twice the area of, let me shade the other rectangle, triangle with blue, is twice the area of a triangle shaded with blue. All right, so the area of a rectangle in red is twice the area of blue. The exact same thing happens on the other side. And now when we add these together, we can see that the area of a big rectangle over here is, so the area of a big rectangle is simply a big rectangle, meaning the one that I'm going to draw with blue right now, is simply base times height for where the base is the segment AB and height is the segment what do I have here? So you know what? Let's call the base. Let's call it B so we can use some easier. Yeah, let's call the base. Yeah, let's call the base B here. I'm gonna say B over here, where B is this much, right? That's B, and height is this much over here, H. So height is so base times height would be the area of a rectangle there. But this is equal to, as we saw, our triangle breaks up in two, and each of them has a congruent part on the other side, on the missing side. So our triangle is basically, the area of our triangle is half of the area of a rectangle. So twice the area of a triangle ABC. So that gives us that way we derive a formula of area of a triangle ABC as base times height over 2. All right, so that is the the resolution for the area of a triangle, and you see it's not that particularly simple. So you have to come up with this extra extra auxiliary construction that helps you incorporate your triangle as part of a rectangle, and then the rectangle what the area is because you already defined that earlier. So what's going to happen in general if you have some more complex structures? If you have some more complex structures like polygons like this, then your only hope is to really break those up as a bunch of triangles and then calculate the area of each of the triangles. And even that is not, I mean, that's easy to do because now we know the area of a triangle, but even that is not sufficient because you have shapes that are not necessarily triangles like this one or polygons like this one. This is a circle, right? And this was the first challenging problem that really so now there's a debate on that. But this was a problem that really mathematicians couldn't come up with a rigorous solution for it for a long, long time, thousands of years. And the rigorous solution we will be able to more or less, if we push things a little bit here, we would be able to give a rigorous solution in this class for why the area of a circle, which you all memorize as pi r squared, why is the area of a circle pi r squared? I remember I memorized it when I was a student. I had no idea why the area would be pi r squared. Luckily, calculus has the answer for that. So that's one of the things here that we deal with. Now, what would your approach be if you were trying to calculate the area of a circle? Well, it's a bit tricky. So what people normally do, they say, you know what, let's split up this circle in a very in a bunch of let's put a polygon, a regular polygon, very very close to the circle, you know, with many sides. And let's approximate the area of a circle with the area of this polygon. And for the polygon, we know what to do because we figured out here on the left side. And that's a valid approach. And that way, people manage to calculate the area. But now, if you look at this approach here, this is an approximation. So, to make things rigorous, what do we do with these approximations? We go to the limit. So what do we do in general? We would divide this circle into smaller and smaller pieces, right? And we approximate each of them with a straight line segment. Then we calculate the area of a corresponding polygon. This is the process, this is the key, this is the germ that led to the definition of a definite integral, which we are going to calculate in the coming lessons. And that led to the concept of, you know, area being discussed the way we discuss it here. So let's take another look. All right, so what we need right now is, and this is a very ambitious project, let's take a random function like that, and let's calculate the area under that function. Because if we know how to do that for a random function, of course, the circle has an equation, at least half of that has an equation as a function, and there's other things, and in fact, every other thing that we know of can be broken down like that as a bunch of areas under the graph of a function. So now let's remember what we did for the circle, right? We split up the circumference into smaller segments, small segments like that, and you know, for each of them we calculated an area like this, and that will be the valid approach here. Except that even this is kind of complicated because you know, if you work with trapezoids, you know, generally, that's not very pleasant. So we might as well try to work with rectangles. So instead of that, I'm going to do the exact same thing, but I'm going to do that with rectangles. So with rectangles, we are going to go, and again, we take the area between, now I apologize, the pictures are not really identical, but you get the idea, folks. So let's say we have a number A here and a number B here. And what you do instead, because this is a function, y equals f of x, you're going to split up this, segment from A to B into small segments. And instead of taking, like we did earlier, trapezoids to approximate the area under the graph here, what we're going to take is actually rectangles. I'm going to take rectangles, something like this rectangle and then this rectangle. And then, maybe there's a rectangle here like that. And then maybe that. And then maybe that. And so on and so forth. So you go all the way up to where you hit the graph and you take the rectangle underneath. And there are two questions here. So we're kind of losing a little bit of area when we do that. Because in contrast with the previous example, in this example, we have a little more white space left here between the rectangles and the graph. If we increase the number of segments here, does that white area kind of vanish eventually or not? Because you wanna know if there's maybe like a skinny area left there. Is there any skinny area or does that vanish entirely? So that's the thing that we're looking at here. And then the second thing, okay, well, so if you split up the area like this, it's not like for a regular polygon. If we have a regular polygon here, we can control the areas here because we know the number of sides, the number of sides of a polygon, and we know the angle there, so we can kind of say what the area of a triangle, the radius of a circle remain constant. Over here, we have a bunch of rectangles that really we have not much control on. And how do we actually calculate, we can increase their numbers. How do we calculate the limit as maybe that number goes to infinity if we somehow are able to show that this white area here goes to zero? How are we going to be able to calculate this limit? Well, those are both valid questions and they're very good questions. And literally, so the first question is very difficult to show that the white areas, go to zero, even when we increase the numbers here. So because when you increase the number, you add more white areas, right? But the thing is, they all decrease. The thing is, do they decrease sufficiently quickly to really go to zero, no matter how many I take? And the question is, the answer is yes. It's a difficult question. So this was answered by the German mathematician Riemann. So Riemann essentially solved the problem that we're looking at here. And then the next thing is well, so how do you calculate? And again, Riemann came up with a solution to calculate that. That's called the fundamental theorem of calculus. So our goal here is not to prove these facts because these facts are difficult to prove. Our goal here is to actually understand how to do this in practice. Now, pay attention here, folks, because this is important, an important issue to understand. This is not how we will eventually evaluate the area under the graph of a function, because this would be complete masochism, to work with the areas and break them up and calculate and such. Somebody has done that already. So what we are going to do is we are going to derive some simple shortcuts like we did those for limits, where we will be able to evaluate these limits in these integrals, these areas, in a very simple way. And I'm going to disclose the secret tool that we use to do that. The secret tool that we use to do that is the antiderivatives. So those antiderivatives, we work so hard to, understand them and calculate and such, will be the key tool to the key to calculate these areas under a certain graph. Now, until then, though, we are going to follow the historical development of these notions. So for another lesson or so, we are going to focus, folks, on calculating, on estimating, not calculating, estimating areas under the graph by using approximations with rectangles like this. And the problem that I like to do here is the following. Let's take the function f of x equal to, and that's going to be 1 plus x squared. So let me see. Okay. Yeah. Let's take this function 1 plus x squared, or x squared plus 1. And if you look at the graph of this function, I'm not going to pull Desmos here, but you can check in Desmos quickly. Let me draw a quick picture of this function. So this function would look like something like this here, folks. There we go. There we go. So that. And the function, the graph that we see over here is of course there's an area under the graph, and let's say we want to calculate the area from 0 to 3 over here. So now my scale is not very good here. It's obvious that I cannot scale it properly because this number will be very large. In fact, the point where I'm intersecting the graph here is 3 squared plus 1. So that's going to be 3 comma 10. That's going to be the number here. And, just to have an approximation, just a fun exercise, let's divide this interval in 3 equal parts. And let's calculate, let's take a rectangle that touches the graph here. And it's going to be this one. And let's take another rectangle that touches the graph here, and it's going to be this one. And let's take another rectangle that touches the graph, and it's going to be this one over here. All right, so with these things, folks, we are going to calculate the area under the graph. We're going to estimate that by estimating the areas of these rectangles. So now to estimate the areas of these rectangles, I'm going to have to estimate where their corners are. That's the important thing, because we need the height of each of them. The base for each of them is 1, so it's very easy to do. And I'm going to say, okay, so this corner over here, the one here is to the value of this function above 2. So remember, the equation is y equals x squared plus 1. If we plug in 2 in this formula, 2 squared plus 1 is 5. So this point is 2 comma 5. And this one point here is 1 comma, and 1 squared plus 1 is 2, 1 comma 2. And this is, okay, over here, that's 0, 1. So folks, these are the areas, are the key points. And now I'm going to write the numbers of these areas. The area height 1, base 1. So the area is going to be 1 here. Over here, height 2 and base 1. The area is going to be 2. And over here, height 5 and base 1. And the area is going to be 5. So without much effort, folks, we can say that the area under the graph of y equals x squared plus 1 is approximately 1 plus 2 plus 5, which ends up being 8. All right, folks, so that's the final result for the area. Now, this is not perfect. and it's actually a little far from reality. It's a little bigger than that, but not significantly bigger. So we actually are going to learn of a quick way to calculate this area properly, but again, for the time being, this is a good exercise to complete. So we approximated the area under the graph. Now, generally, they tell you in the book a complicated formula. So if you look here at the segments A, B, and the rectangles that you have here, you can call this, if you fancy to do a bunch of abstract math, you can call this point x sub 0, the one at A, and then the next one, the one next to him, the one next to that x sub 1, and one next to him x sub 2, and the one next to him x sub 3, and so on. So all the way to over here. And the thing is, you can write the bases of these rectangles, you can write their base is x sub n minus x sub n minus 1. So the difference of two consecutive, subdivision points, if you want. Now, in the book, they also use notation delta x for these subdivisions. That to be the base of a rectangle. And the area of a rectangle, the area of a subdivision rectangle, something like this here, would be some value of f at one of the corners. So let's say at x sub n times a delta x like this. So that will be the area of a rectangle. So that will be, the thing that you would have here. All right, so that will be the area. And then what we calculate here when we approximate the area of a function, we calculate a limit as this number n goes to infinity. So when you make a subdivision with many parts like this, of a sum like this that is f of, let's say, x sub 1 times delta x1, let's say, or delta x plus f of x sub 2 times delta x. So this would be the area of a first rectangle. This would be the area of a second rectangle plus plus f of x sub n, times delta x. So this would be the formula that they give you in the book. This is called the Riemann sum. And in practice boils down to doing something like the example that we did earlier here. So basically discovering the rectangles under the graph and calculating their areas properly and adding them up. So in the coming days, we are not going to use this formula again in this abstract form because that confuses a lot of people. So what I'm going to do concrete examples of areas under the graph like this. We're going to calculate a bunch of those to kind of see what they look like. Now, Riemann discovered a number of interesting things, and I'm going to just briefly tell you right now, and we're going to close the lesson. He discovered that if you can allow these rectangles, the ones under the graph, to actually go above the graph, provided that the top side of a rectangle, it touches somewhere the portion of the graph that I'm interested to assess in terms of area. So you could have, instead of this rectangle here, you could have one here, and that's still because there is this touching point that's altogether, that's still going to be a good one to calculate an approximation of the area. If you take many of these and make them small, at the end of the day, you're going to get the correct area regardless where you place this top side. We like to put the top side just to be under the graph to kind of be for clarity. But again, you can put it anywhere you really want as long as it touches the graph properly. So that's what Riemann discovered. And then this exciting part, but again, a little abstract and a little, on the artsy side of things. So you will, you would see this again if you were to take 2 levels of calculus, of advanced calculus, Unfortunately, we only offer one level of advanced calculus, so most likely you'll never see this again in a future class, except for calculus 3, I would say, where you would generalize, extend this concept to 3D measures. So that being said, folks, I'm going to close the lesson here. We're going to come back and we'll discuss more about these with some concrete examples. I don't want to leave you hanging with this because this is a little abstract. We'll do some concrete examples tomorrow and the day after tomorrow. All right, thanks for watching the class here. I'm going to stop sharing these, folks.